Hello and welcome. So this week's article will be a review written by Kemal, Ishmael, and Amin. It is titled "Molecular Links Between Circadian Rhythm Disruption, Melatonin, and Neurodegenerative Diseases," and it is a review. As I stated earlier, this paper was published in 2025. So here is the abstract. If you just want to pause and maybe read it, but I'll just kind of touch on the little last sentence here, which it says that review provides recent findings from the past 5 years and highlights how circadian dysregulation mediates key molecular and cellular disturbances and the translational potential of circadian-based therapies to help with neurodegenerative diseases. So, what is circadian rhythm? So, circadian rhythm basically is internal or intrinsic biological cycles that follow an approximate 24-hour period. They regulate a wide array of biological activities, psychological functions involving processes like the regulation of sleep timing, hormonal balance, metabolic activity, and cognitive functions. And at the systemic level, what is the kind of the most important thing that we need to know that activates the system? Something called the suprachiasmatic nucleus, or more commonly known as the internal clock. And it is in the hypothalamus, and it functions as the primary coordinator of circadian rhythm. It aligns peripheral clocks located throughout the body and light input that comes from the retinal ganglion cells within the retina and trains the CSN. And this ensures that there is synchronization with external environmental cues. And this is the first thing that I'm going to discuss here. One thing that I should kind of explain as to why it's important that we have a good circadian rhythm is that when you have fragmented sleep or altered melatonin secretion, which is a hormone that is associated with circadian rhythm, you have a disruption in core body temperature and you have irregular motor activity. So I'm just gonna get true to the presentation here. So as you can see here, healthy brain, normal circadian rhythm, you have a healthy neuron as well. In neurodegenerative diseases, there's other mainstream things that are happening. But you also have the aberrant and dysfunctional circadian rhythm, and then you have the disease neuron that is littered with plaques and other aberrant proteins and probably inflamed, as they can already tell here. So it's going through a lot of problems, and most likely the person who is holding who has this type of neuron is not having a great time with it. So here is another illustration that kind of explains most of the proteins or molecules that are associated with circadian rhythm. Starting with the suprachiasmatic nucleus, we have the peripheral clocks. These are the things that are inside all throughout our body. COLK, which is the nucleus, BML1, which is also the nucleus, is our transcription factors. PER 1 to 3, which are transcriptional repressors. CRY, which is also the nucleus, is a transcriptional repressor. Okay, so there's a difference between cytoplasm nucleus and nucleus. So in the nucleus, it's kind of this is where the genes are. The nucleus, usually it's called the nucleolus, but the cytoplasm nucleus is kind of the generic nucleus we know within each body, within each cell. Um, and then you have the CK1 theta and epsilon. Looks like that's epsilon, which is in the cytoplasm, which is a type of enzyme. We have REV alpha, which is in the nucleus. We also have ROR alpha, which is also nucleus. These are all that one is a repressor and another one's an activator. Here you see, so TTFL is transcriptional translational feedback loops. They influenced by feeding, temperature, and glucocorticoids. Dimerizes with BM clock usually would come together with BML1, and then they activate the PER and CRY, as well as CRY proteins. Initiate circadian, and what their main function is to initiate circadian transcription. PER1 phosphorylated by CK1 theta and epsilon, goes into the nucleus and is able to inhibit clock BML. CRY stabilizes PER, part of the inhibitory complexes that stops clock BML1. This, as it already explained, it kind of helps with this whole process here. You can just kind of pause this, and if you want to look at it, I don't want to really explain everything if it's all here. So if you just want to look at it, go ahead. So how does this entire system work here? So we have the activation of SCN, which is usually promoted by the darkness that comes from the retinal ganglion cells, the darkness stimulation from retinal ganglion cells. And what happens is essentially when it's activated, there is calcium influx within the cell that causes the phosphorylation of a molecule known as CEMP, or cyclic adenine monophosphate, which binds with CREB, which is it's a nucleolus translocator. This activates clock plus BML1, which are dimers. The clock BML1 goes into the uh, genes, and it helps transcribe the PER1, PER2, and PER3, as well as cytochrome. So PER and cytochrome can come together, and then they inhibit clock BML1 transcription. The other thing is we have the REV, ERB, and ROR complexes, which modulate the production of BMAL1. BMAL stands for brain and muscle ARNT like one um, protein, and these are basically like transcriptional activators and repressors. Both of them will basically produce BMAL1. So we have BML clock coming into the nucleolus. It binds into the protein, and then it produces the release of circadian clock genes, which include PER and CRY and CRY, which have the capacity to come and block BMAL and clock. And then you have the addition of the ROR, which is basically it's a response element, and this with REVRB are able to produce BMAL, which can go on and dimerize the clock and kind of form a feedback loop. So usually when BML and clock are already bound here, and they've already released, and the PRCRYs have already been translocated outside of the protein or outside of the nucleolus, likely there's not going to be as much more transcription essentially. So that it's a positive feedback loop that leads to a negative feedback loop. BML1 is going to be kind of important as we go on, because it seems that when it is decreased, it impairs mitochondrial biogenesis, leads to increased reactive oxygen species, and it impairs synaptic vesicle cycling, as well as increasing susceptibility to oxidative damage and inflammation. Okay, hopefully that kind of makes sense. We can just go back to the article and we can touch more exactly of what is the most important, what's the most important hormone here, which is known as melatonin. This kind of just explain all the complexes that I just explained here. And this is the illustration that we saw earlier. Okay, now let's talk about melatonin. So this is released in the pineal gland at night, crucial for stabilizing biological rhythms and aligning peripheral clocks with the suprachiasmatic nucleus. This is synthesized in a multi-step pathway starting with tryptophan, an essential amino acid, and it undergoes all these processes, and this kind of this is basically just explaining further of how this thing is created, how melatonin is created. So its physiological actions are through two high affinity G protein coupled receptors. We have melatonin receptor 1A and 1B, widely expressed in both central and peripheral tissues, and primarily involved in acute suppression of neuronal firing. This contributes to sleep promotion, phase regulation, and MT2 is basically involved in circadian timing as well as realignment of misaligned biological clocks. So usually that's kind of the adapting function of melatonin here. Okay, and why is this important? So beyond the canonical roles in circadian rhythm regulation, this receptors initiate several intracellular signaling cascades that are critical in involving molecular pathogenesis of neurodegenerative diseases. So one key pathway is phosphatidylacetyl 3 kinase and protein kinase B, where receptor activation leads to phosphorylation, and subsequent inhibition of glycogen synthesis, kinase 3 beta, which is involved in tau protein hyperphosphorylation and amyloid beta accumulation. I have a little tidbit here about why that is. So, abnormal activity of this protein seems to be linked to Alzheimer's and Parkinson's disease. So, it's important to know that melatonin kind of stops that from happening. There's an illustration here that I have further details on. Maybe you can take this. So, as we talked about earlier, dark stimulation increases the availability of melatonin. Melatonin goes into its receptor, and it has the capacity to basically block this um, enzyme from doing its action, which include forming neurofibrillary tangles and amyloid beta accumulation. It also activates other pathways that would essentially lead to the reduction of mitochondrial dysfunction, as well as oxidative stress, as well as it prevents the accumulation of inflammasomes, which tend to cause inflammation within the neuron. Another thing that melatonin does is it upregulates tight junction proteins known as, it's in this paper here. So it upregulates tight junction proteins known as clodin 5, ZO1, and L-clodin. And this upregulates tight junction proteins and enhances structural integrity of blood-brain barrier. SARS-CoV-2 neuroinvasion model, in vivo and in vitro mice and human cells were given melatonin, and it led to inhibition of ACE2 mediated viral entry. This reduced AB related burden. Another thing is in gastric cell line in vitro, these are human cells. Metalloproteins. This inhibits the extracellular matrix degradation via IMPK activation, and this improves BBB stability. And in other mice models where the induced LPS, which is a toxic agent that's given to rats to kind of cause like a sickness signaling, and the target pathway of melatonin was AMPK, and activation of AMPK reduced inflammation, stabilized tight junctions, and also restored blood-brain barrier integrity under inflammatory conditions. So you can see this is a very important hormone within the body, and if it goes awry, you can see how all these things are going to be affected, and how when you have further burden of amyloid beta and neurofibrillary tangles mucking up the brain, you have this disruption as well. The brain is just kind of going through a different type of war that's most likely not going to be resolved very easily. Another thing that they talked on here is that reduced neuronal synchronization, impaired response to light, and diminished expression to light genes of BML1, PR2, and CRY1. Disruption of circadian rhythms comes with impaired mitochondrial performance, which leads to release of reactive oxygen species and low-level inflammation that may accelerate neurodegenerative disease. 146 human samples were taken, and 1,000 transcripts were with age-related changes to circadian patterns. Decreased in BML1 and PR2 was seen in these genes. So these are people who are undergoing who already had the neurodegenerative pathology within their head, or phenotype within their head, and that is what they saw. They saw a decrease in BML1 and PR2 expression. Further, BML1, PR2, and REVRB exhibit disease-specific alteration in expression patterns. So, in patients with AD, PD, and Huntington's disease, in Alzheimer's disease, diurnal fluctuations in melatonin correlate with cognitive decline and serve as prognostic indicators of disease progression. So, the further they are in disease, the worse their melatonin burden usually is. Circadian dysfunction manifests early as REM sleep disturbance. So, in people who are not able to kind of control themselves when they're sleeping, especially if they have an AD phenotype, usually that kind of tells a researcher or the doctor that their melatonin burden is kind of in a very bad state. And another thing to also take here is that if you don't have if you have early life visual impairment, the risk of having AD is also increased. So if you never get to kind of train your suprachiasmatic nucleus in an early age, the chances of you having AD are kind of increased because of that. Okay, so yeah, these are just kind of all the studies that are looking at and explaining why melatonin is very important for the brain. All right, so I'm going to touch on why circadian dysregulation and melatonin are in AD. So, most common form of dementia is frequently accompanied by circadian rhythm disturbances, right? So, we have sleep-wake disruptions preceding the onset of cognitive symptoms. These alterations, characterized by fragmented sleep and amplitude, forget about this, reduced amplitude circuit. That's kind of like it's based on sleep studies that look at the amplitudes of people who have Alzheimer's disease versus those who don't, and the amplitudes tend to be very different. So, what I want to touch on here is that circadian disturbances in AD are associated with reduced expression of neurotrophic factors such as BDNF. That's brain-derived neurotrophic factor, which tends to be released in normal brains to promote the health of neurons. Usually, in people who have neurodegenerative disease, this is kind of completely aberrant, and it it is it's not there because of the entire the cascading effect of the death of neurons that's occurring within these neurons, unfortunately. So, clinical studies further highlighted melatonin's therapeutic potential. Randomized trial to the Netherlands involving nearly 200 elderly nursing home residents, 86, showed that 15 month regimen combining 2.5 milligram melatonin with daytime bright light therapy significantly reduced agitation, improved sleep quality, but the findings were not consistent, unfortunately. So, a growing body of research here implicates melatonin in the regulation of lymphatic function, a sleep dependent clearance system responsible for removing interstitial waste, including amyloid beta. The lymphatic pathway involves CSF influx through periarterial spaces, interstitial exchange, and efflux via perivenous routes. So these are like peri meaning side, venous meaning vein. Aquaporin 4, expressing astrocytes, played a critical role in the system, and melatonin appeared to enhance its function by improving AQP4 polarization in rodent models of chronic stress. Melatonin administration restored integrity and normalized waste clearance. Moreover, melatonin suppression of orexin, an arousal promoting neuropeptide, may support lymphatic efficacy by promoting deeper sleep and reducing nocturnal sympathetic activity. Yeah, you could see that AD is also impacted, or melatonin dysfunction is impacted in a lot of neurodegenerative diseases, such as Parkinson's disease, Huntington disease. We also have multiple sclerosis and ALS. So this table kind of just explains exactly what was explained in most of these studies about how melatonin and light therapy may kind of help with managing the symptoms of these diseases. And now I want to touch on the gut brain clock axis, which was not known, but a little known fact is that melatonin is actually derived from serotonin. And serotonin comes from tryptophan derived microbiome metabolites such as indole derivatives, regulated melatonin biosynthesis, and gut brain signaling. These forms key nodes in the circadian microbiota axis. So having a good microbiome is kind of important in having good melatonin synthesis, right? So melatonin is produced by the gastrointestinal system, and it's essential in maintaining structural integrity within the intestinal barrier and modulating host microbiome communication. The gut microbiota contributes to melatonin biosynthesis via tryptophan metabolism, and the species that are more specific for this are Lactobacillus and Clostridium, and they kind of produce indole 3 acetaldehyde and indole 3 propionic, which are precursors to melatonin synthesis. So obviously, knowing that disruption of this is going to cause some problems, and that includes dysbiosis, declining of melatonin production, and onset of neuroinflammatory states, highlighting a potential risk link between gut health and neurological function. Melatonin was reported to exert modulatory effects in circadian gene expression in the gut, which in turn can influence microbial rhythmicity, metabolic output. In aged mice exposed to light at night, conditioned melatonin supplementation not only restored gut microbial rhythm, but also reduced intestinal inflammation and blood-brain barrier permeability. Another important thing here is that nutrition is very important in upsetting this. As I said here, that time restricted eating, early time restricted feeding, and intermittent fasting were shown to restore rhythmic gene expression, improving metabolic flexibility and reducing neuroinflammation. All right, so here they kind of just talk about how melatonin analogs are kind of important in therapy. Agmelatine is one of those analogs, and this was able to resynchronize or cause resynchronization when you lost the synchrony, and also had antidepressant activity, increased dopamine and norepinephrine release in the frontal cortex, property absent in melatonin. Another one is tazimulton, which was had a role in circadian phase shifting, approved for non 24-hour sleep-wake disorder, especially in blind individuals, and exhibits a longer half-life. So people who kind of were born blind can probably depend on this one. These analogs offer great receptor subtype selectivity and good bioavailability, so they last longer than melatonin, and they enhance their clinical utility in specific circadian. What I did say earlier is that some of the drugs that are used, some of the melatonin drugs that are used now, they don't have a lot of bioavailability, so they're not able to exact the potent effects of the endogenous melatonin that we have. So it's good to know that there's some drugs that are kind of like working towards increasing that bioavailability component. So, a little caveat here is that studies utilized melatonin doses between 40 and 100. Future research should aim at formulation improvements, chronopharmacological timing, and biomarker guided certification to fully leverage the therapeutic potential of melatonin agents. Drug timing is important. So here, one more thing here. So several classes of neuroactive drugs demonstrate time-dependent efficacy. For instance, the administration of acetylcholinesterase inhibitors, such as Nonzepil, in the morning, was associated with improved behavioral outcomes and reduced sleep disturbances in AD patients. Similarly, timing the monoxidase B inhibitors like selegiline influence dopaminergic tone and motor symptoms control in PD. So it's important. They stated as well that when you pair these things together, you tend to have a better work. So in AD and mild cognitive impairment, melatonin given alongside cholinesterase inhibitors such as nonazepam improved cognitive performance, sleep quality, and reduced depressive symptoms, supporting its use as an adjunctive chronotherapeutic agent. Furthermore, they looked at more specific molecules or the transcription regulators that we talked about earlier and seeing how, if activating them, what would come from it. And those ones include ROR alpha, REV, ERB alpha, and SIRT1. And when they activated them using certain analogs to them, they found that REV, ERB alpha specifically, when you activate it with a derivative or a analog, you attenuate neuroinflammatory cascades and restores circadian rhythms. When you activate SIRT1, this enhances neuronal survival, decreased tau pathology, and improved cognition. Another important thing here that they talked about was ROR alpha, which decreased microglial activation, increased anti-inflammatory signaling, and protected synaptic integrity. Another, I guess it's kind of like a new age thing, was music therapy. This was shown to be neuroprotective, stabilized circadian rhythms, and mitigated disease progression. Music therapy was investigated to influence not only cognitive and emotional domains, but also neural circuitry involving circadian regulation, thus representing a multifaceted, non-pharmacological intervention. So that's pretty much it for today. Thank you so much for watching, and I hope you guys have a good day.